Mike Wiesner says, howdy to all of Dr. Barth's students, young and old. Paul Burgart says, howdy and happy Monday to all.
Happy Monday indeed.
Yes.
I love this little animation of Gale Crater, both on wet Mars and dry Mars.
Yes.
And they transition again to wet Mars with the water flowing out.
And
we were talking before the show.
Seen Mars with oceans on it. That would have been incredible.
Yeah, we were talking before the show. In basically 1/3 of Earth gravity, the waves would be tremendous. Talk about surfs up.
Yeah.
Gale Crater would be big enough to have a long enough fetch to see waves coming across, and they must have been just spectacular.
Well, I wonder what it would have been like to surf in so much less gravity too. So
yeah, because
you
water's
catch air a lot easier.
Oh yes, and we've seen things with the. Oh, I have my friend here. Hi, Bunter. I have one of my dogs is here in the room. Hi, Val. Yes, you're a good boy. But we have we've had those reports of Martian quakes.
Yeah.
And the Martian quakes could have produced tsunami, and a tsunami on Mars would be formidable indeed. It'd come in and towering waves.
Yeah.
It would just be an amazing phenomena.
Yeah.
To behold.
Really cool.
That would be something I would love to see an animator take on that challenge, animate a tsunami in a Martian ocean.
Sure.
Simulate it with the low gravity. There would be some fair amount of physics to be done, but it would be quite a spectacular animation.
Indeed. Okay. Well, let's get started.
All righty.
Beneath the thin atmosphere of Mars lies an enigma, a desert landscape shaped by flowing water. In the distant past, Mars must have had a warmer, wetter climate, but scientists wonder just how wet was ancient Mars?
So in the ancient past, we have some indications that water was flowing on the surface, but how much water was there? We're talking about oceans, are we talking about small rivers, little rain? So these definitions of how much water was on the planet was very undefined.
A major question has been how much water did Mars actually have when it was young, and how did it lose that water?
To answer this question, a team of researchers at NASA's Goddard Space Flight Center used infrared telescopes on Earth to study water molecules in the Martian atmosphere.
We used the world's 3 major telescopes for infrared astronomy. From the ground, we could actually take a snapshot of the whole hemisphere of the planet on a single night.
The new infrared maps reveal the atmospheric ratio of normal to heavy water molecules at different locations and seasons on Mars. Heavy water molecules contain a heavy isotope of hydrogen called deuterium, which remains trapped in the Martian water cycle, while normal hydrogen is lost to space. The researchers found that water from the polar ice caps is highly enriched in deuterium, indicating that Mars has lost a tremendous quantity of water.
Now we know that Mars water is much more enriched than terrestrial ocean water in the heavy form of water, the deuterated form. Immediately, that permits us to estimate the amount of water Mars has lost since it was young.
The findings indicate that only 13% of an ancient ocean remains on the planet today, now stored in the polar ice caps. 87% of this ocean has been lost to space. This means that early Mars would have looked much different than it does today, with a significant portion of its surface covered by water.
So the really interesting question is, could it form a sea or an ocean? And indeed, it would. In the northern plains, which is a relatively flat region but depressed from the rest of the planet, it would form an ocean that was approximately 20% of the planet's surface area. And so that is a respectable ocean.
This ocean had a maximum depth of around 5,000 feet or around 1 mile deep. It's deep, not as deep as the deepest points of our ocean, but comparable to the average depth of the Mediterranean Sea.
By combining Martian topography with the new estimate for water loss, the researchers were able to simulate Mars's ancient ocean and its escape to space. As Mars lost its atmosphere over billions of years, it lost the pressure and heat needed to keep water liquid, causing the ocean to shrink and recede northward. The remaining water eventually condensed and froze over the north and south poles, giving Mars the ice caps that we see today. This new scenario means that Mars would have stayed wet for longer than previously thought, expanding its ancient habitability.
We now know that Mars was wet for a much longer time than we thought before. Curiosity shows it was wet for 1.5 billion years, already much longer than the period of time needed for life to develop on Earth. And now we see that Mars must have been wet for a period even longer.
It's fascinating that we can learn so much about 4.5 billion years ago what measurements are taken right now. And ultimately we can conclude this idea of an ocean covering 20% of the planet, which opens the idea of habitability and the evolution of life on the planet.
Well, hello everybody, it's Scott Roberts with Explore Scientific and the Explore Alliance, and this is our 44th episode of How Do You Know with Dr. Daniel Barth. This particular episode is very interesting as Dr. Barth talks about the evidence of carbon-12 on the red planet and what that means. What does that discovery actually really mean? And so I'm going to turn it over to Dr. Barth, but the search for life on the red planet is something that's very serious business amongst planetary scientists. It's gone way beyond the kind of tongue-in-cheek, wishful thinking stage to the nuts and bolts. How do we figure this out? It probably existed kind of stage. So, but careful as scientists are. Dr. Barth will navigate through all of that with us today on How Do You Know?
Hey, thanks, Scott, and welcome
Yep.
everybody. This is an exciting episode for me and an exciting discussion. Whenever I have this sort of discussion with students, I always warn them beforehand and say, well, nobody's going to be happy with me at the end of the lecture today. Because this is one of those topics that engenders a lot of questions, but not a lot of answers. Cutting edge science, bleeding edge science, Scott, as you know, is often ambiguous. And we see this and in the history of science, the way it's told in popularized in books and textbooks and stories, in legend, oh, the apple fell on Newton's head and he discovered gravity. Oh, Galileo invented the telescope, the astronomical telescope, and boom, he saw Jupiter and baha, he proved Copernicus was right and the sun was the center of the solar system. It's never that clean cut. It's never that clean. It's never that easy. It's never that nice. And from a couple of centuries afterwards, it all looks simple. It looks easy. It looks obvious, but it's not. Science is very, very messy. And we've talked before, Karl Popper and his ideas about science. Science effectively is a cage match. Different people put up theories and people place their bets, and people make their reputations by shooting at theories and saying, no, bang, bang, that's not right. I poke a hole in your theory. And it really is the last one standing, the crazy cage match with 12 combatants. It's like a gladiatorial combat. And we're seeing this sort of thing today. When we have data which is ambiguous, we find that young people don't like it. Young people are a little more impatient for answers than their senior colleagues. And the young people say, but I want an answer now. What is it? Which one is it? And I'll get this response from many people when I talk, when I speak in public, when I lecture in the classroom. But which one is true, Doc? Which one is true? I say, we just don't know. The other group of people that really don't like it is very senior scientists tend not to like the ambiguity. And not because they're impatient for an answer, but I think often because in their heart, they've already put their money on a particular horse. I think this one's true. And we're going to see some of that today. Let's take a minute, and we usually start with opening comments and a couple of things going on. One, Webb is close to achieving its final temperature, and all the instruments are focusing, and they're all coming up diffraction limited, which is
Awesome.
It's astounding. If you're not a telescope nerd, diffraction limited is the theoretical limit of resolution, and there are equations for this. Theoretically, a lens or a mirror of a certain diameter should be able to achieve a certain degree of resolution. They should be able to separate things which are this close or see things which are this tiny. Webb is coming in right at the theoretical limit, which is astounding. Hubble doesn't do this. The Keck doesn't do this. The big telescopes around the world, the famous telescopes, Palomar, the Hooker, they're not at diffraction limit. They're very good, but are they at the theoretical limit? Not really, but Webb seems to be pretty close, which is so exciting. And we're going to be seeing great things. The other fascinating thing, and we may have a show coming up on this sometime in future, depends how the story develops. Scott, you posted this on social media in the last week or so. Micronovae. We've found a new kind of nova on white dwarf stars, and they seem to explode only at the poles. Bang,
bang.
And it's kind of weird. We always think of nova and supernova as being a very destructive process that occurs across an entire star and sometimes destroys stars. And now we're seeing these little micronovae, and it's got a little pressure valve, pop, 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 that may relieve the pressure and keep them from going bang. And so this is a fascinating story, and this undoubtedly will continue to develop. Perhaps less globally interesting, but I hope interesting to our audience. The new book, Star Mentor. The process of publishing is very complex. You submit a manuscript, they accept it. You work with an editor for months. Should we change this? Should we change that? You finally agree. They send you a mock-up of the book called a galley proof. And you go through line by line and you make all the corrections. You fix all the things you missed before. And then they send you a set of corrected galley proofs. And you're supposed to go through and say, is everything okay? And this week, I got through the corrected galley proofs and sent them back to Springer, my publisher, and they're starting the production process. So for those of you who have pre-ordered, the book is now in production. It will be in your hands very soon. Scott and I are talking about some sort of book giveaway for the 50th show of How Do You Know, which should coincide with the books being available. And we'll figure out how many we're going to give away, and we'll see that everybody who gets one gets a signed copy. And you can tell me what kind of thing you would like to have. Yeah, right. What you would like in there. To my best friend. So anyway, so these are things that are going forward. So let's go ahead and talk about our show today, which is entitled Carbon Signals on Mars. And this is kind of a companion piece to last week's show about the oldest life on Mars. And we talked last week about the oldest life, and there's a debate. The scientists in Canada looking at the fossils they claim they have found in Ontario. And they say these are microbial colonies. And we have reasons that we think so. And one of the primary indications that they're saying, our fossils are enriched in carbon-12. Well, what are we talking about here? Let's just back up a bit and tell people about isotopes. I'm sure many of our viewers know, but just to review. An isotope, you can have atoms, and atoms have protons and neutrons in the nucleus. And it's the number of protons that make the atom's identity. So if you have 3 protons, you're lithium. If you have 8, you're oxygen. If you have 12, you're carbon, and so on. Well, the number of neutrons is more flexible. The number of neutrons can change. We can have carbon-12, which means you have, carbon is element 6. I made a mistake. You have 6 protons, 6 neutrons. You can have carbon-13, which means 6 protons, 7 neutrons. Well, how does this change anything? Chemically, it doesn't. There is no chemical test we know of with a reagent and how it performs in a chemical reaction, which says, gee, is this carbon-12 or carbon-13? The changes we see are 2. There are 2 primary things that are different between 2 isotopes. The first is isotopes weigh differently. Carbon-12 and carbon-13, carbon-13 weighs about 7% more. On the other hand, it is the difference of the 1 more neutron, right? When you're only talking 12 atomic particles, and now you add a 13th, you've changed it by a few percent. And there are other isotopes of carbon. 12 and 13 are the most common. But the other thing, the thing that interested atomic scientists in the early 20th and mid-20th century is different radioactive processes. We refer to today, we say different isotopes have different stability. What's the half-life of an atom? How long does it take before radioactively something goes pop and the nucleus changes? Carbon-13 is more radioactive and therefore less stable than carbon-14. And we talk about carbon dating, and that's with carbon-13, and it decays over time. A sample of carbon-13 will last about 50 to 55,000 years before it decays and all the nuclei change from carbon into something else. So we have this radioactivity difference. And there are a few other things if you get to talking about fusion and fission and different things like that. But let's avoid the tricky stuff. Let's just talk about 2 differences primarily. 1, the isotopes weigh different amounts, and 2, the isotopes react differently in terms of their radioactivity. Well, for some reason, and we have no idea why, biological processes prefer carbon-12 quite strongly over carbon-13. So if you take a look at, if you went down to your grocer and you bought a flat of chicken legs, and you take those chicken legs to a lab and you say, test the carbon, you're going to get a ratio of carbon-12 to carbon-13, and you're going to get more carbon-12 on average than if you took a sample of, say, soot from a fire or carbon that's in soil. And you take a look, you take a scoop of soil and from your backyard and you say, let's do the carbon-12, carbon-13. And even on Earth's soil is very, there's a lot of life in soil. There's a lot of microbes and nematodes and burrowing animals and all sorts of crazy things. But if you take a sample of just carbon from that you've dug up, and we won't say coal because coal is a biological product, but we'll say you take a sample of carbon and you look at it and the carbon-12-13 ratio in nature, and then you take a look at a biological sample and the carbon-12 is a higher percentage. And you can imagine that, oh, well, if you were a biological cell, incorporating a less radioactive form of carbon might be healthy. And you can see why that might have been evolutionary, that ability would be selected for evolutionarily. But as for the process, because keep in mind that all biological processes are fundamentally chemical processes. So somehow the chemistry in a cell prefers carbon-12.
Yeah.
This is so universally true that on Earth, when we see something with a atypical high carbon 12 percentage, we say, aha, this thing came from life. And we can find that many ways. If we talk about a fossil, oh, the materials used to be cells. If we talk about things like coal that we dig out of the ground, okay, these are decayed plant remains. And they at one time were biological. Anytime we see this skewed carbon 12, carbon 13 ratio on Earth, this is pretty much the gold standard test for yes, this was a biological sample. The Canadian scientists who were taking the samples from Ontario, they looked at their samples and they say, one of the ways we know these are biological is we see this skewed carbon 12 ratio, the enhanced carbon 12. Well, we take a look at another really old place on Earth, the Tumbiana Formation in Australia. And my Australian friends, I hope I'm saying that correctly. And I don't know if that's an Australian term or if it's an Aboriginal term or if it's a scientific term. I didn't have time to look it up. But the Tumbiana Formation, they found stromatolites. Stromatolite is a fossil from a microbial mat. Think about pond scum, not plants, not even algae, but just a layer of bacteria. If you've ever taken a slice of lunch meat out of the fridge and you realize, ooh, it has that slimy layer on top of it, and this isn't good, I'm not putting it in my sandwich. Exactly. And we're all like, don't eat this. Well, that slimy layer, that's the kind of a bacterial layer we're talking about. And in ancient Earth, we're talking 3.5 to 4 billion years ago. Yes, in these wet, sheltered places on Earth, you would have had these layers of bacteria. And some of these fossilized, and we call them stromatolites. And we can see that in stromatolites, the cells have enhanced and concentrated both carbon 12 and strontium 87, as opposed to the more radioactive forms, carbon 13 and strontium 86. And so life prefers the less radioactive version, which healthy choice, early bacteria, well played, incorporating the non-radioactive isotopes. And it's considered what we call a biosignature. We know of no geologic process that does this. That's not to say there isn't one. It's just if you've said to someone, come up with a chemical reaction in a laboratory that artificially concentrates one kind of isotope over another, doesn't exist. And if you go to industrial applications where we have wanted to concentrate isotopes, and most famously fissile materials for nuclear power plants, nuclear weapons, and in the early Manhattan Project, and in the Hanford nuclear plant in Washington, they had gigantic centrifuges, and they were using centrifuges to separate out lighter isotopes from heavier ones. And so they were using this massive industrial process. And the reason they chose a massive, expensive, complex industrial process is because they didn't know of any sort of chemical process, and we still don't. But biology somehow does it. Although there's a Nobel Prize waiting for you, friends, neighbors, youngsters, if you could find a biological way to concentrate particular isotopes, wow, that would be a huge win. Certainly any sort of fusion where you want deuterium or tritium and you want it for fusion reactor. If you could find a way to separate this out from seawater biologically, wow, what a huge win that would be. And I'm sure there are genetic engineering companies who would love to patent that bacteria, algae, or whatever that would do that. That would be, wow, that would be an amazing, that would be a huge billion-dollar discovery. So right now, we realize there's this interesting biological signature. And on Earth, it is the gold standard. However,
Okay.
something scientists warn us
So
about.
there's no
all the time.
other forms of carbon or anything else except for carbon-12 that indicate life?
Um, right. If you're looking at, if we're talking Earth now,
Yeah, Earth.
one of the ways the Canadian scientists looked, they said, look, there's microtubules, and tubules, right, very fine tube type things. They indicate, we've all seen this in high school biology, haven't we? The strings of single-celled animals, right? The most simple multi-complex multicellular units are these long strings of algae. I think Volvox, if I'm remembering my biology correct, somebody can check that for me.
Volvox
It's a kind of it's a kind of algae that little cells strung together in a line. Well, you form these tubules, and we say, oh, these are from cells, and we can tell, oh, they're the right size. Well, interestingly, the very primitive, what are claimed to be microbial mats, let's be very correct, they have these very fine microtubules, finer than we would see from modern cells. Modern cells are bigger. Well, you look at the Martian meteorite, the Allen Hills meteorite. One of the claims there, oh, look, tubules, fossilized tubules, and they claim that there are other processes that are, and other people argue no. So this is there's very hot debate. Nobody's settled this yet. And I suspect with this single sample, with this single meteorite, we're not going to. There are people who have staked out a claim to each side. Yes, this has fossilized ancient Martian life. No, this is a geological phenomena. And there are people who are willing to die on both hills today. And when was this announced? 1992, I think.
Oh,
President
not
Clinton.
too long ago.
Yeah, so wow, okay, 30 years ago, and there's still no consensus in the scientific community. But consensus doesn't make a darn bit of difference. Galileo had no consensus, Copernicus had no consensus, Einstein had no consensus. They were all right. And we just need to be patient and hope the data comes in our lifetime to satisfy our curiosity. So we see this, let me be clear. There are two caveats I want to make clear before we go further. The first one is no one has discovered anything like a fossilized microstructure that anyone even claims is biotic on Mars. Nobody has a sample from a little microscope on one of the rovers that they're going, ooh, look, it's a microtubule, it's a fossil, it looks like a bug or trilobite, or nothing like that. Nothing like that has been found. Zero. The second thing that I will put out there, and scientists tell us this all the time, we are tremendously biased because we've spent our whole life on this planet.
Yes.
And our entire history of science throughout the world, every culture, has been based on this planet. And if exploration of other worlds has shown us anything, it's that other planets aren't like Earth. We see all this classic science fiction where they land the rocket, they climb out, and they're just there in their uniform with their ray gun. And, no. And then they meet the, the people from the other planet who are, bipedal and bilaterally symmetrical, and they look like us with the makeup on. Right. And if we've learned anything, other planets are different. Mars is kind of unique because it's so close, but the moon is very different. Places like Europa and Io are wildly different. Jupiter, Mercury, other planets are wildly different from us. And there are scientists who say, don't be Earth biased. Other biology on other planets, when we discover it, if we discover it, you want to be very conservative about it, is unlikely to be like Earth. Okay. But there's the other argument, which these are all suppositions. None of these are based in data. The other supposition is that life is self-assembling. Stars are self-assembling. We know this. You have enough hydrogen, one place, enough time, a star will self-assemble. When stars form, they forge new and heavier elements and distribute them. Second generation stars form planets. Planets self-assemble in the dusty disk of material surrounding a new star. Planets self-assemble. And we see all these locally anti-entropic processes. They're not truly anti-entropic because in the long cosmological time spans, everything dies, heat death, okay, second law of thermodynamics, fine. But locally, you can see life selects elements, there's metabolism, there's reproduction, and there's all these anti-entropic processes. Self-assembly is one of those interesting things. So the question is, and we've talked about this before, is life part of that self-assembly process? If you have the right elements and enough time, warmth, water, proper selection of elements, will life self-assemble? And just recently, we have found in meteorites, you can now get all the basic bases that are required to assemble RNA, DNA are found in asteroids. And so there's question, were early prebiotic materials delivered by impactors? Okay, but is life a process that generates itself more or less automatically by physical processes and physical law, just as stars and planets self-assemble? So if that self-assembly hypothesis is true, would you not expect all kinds of life to be similar, to have DNA and RNA type molecules? Would they be exactly like here? No. But would you expect them to have this helical assembly of base pairs structure if life self-assembles? So there's the, ooh, don't think it can be too much like Earth crowd. And then there's the other crowd of people who say, well, if life self-assembles, wouldn't it be similar to us?
Similar.
Would we not see common threads just as we see common threads in stars and planets? Stars are almost always hydrogen, helium mix,
Yes.
and that mix reflects the concentration of hydrogen and helium in the universe. Planets come in a variety of forms. There's the terrestrial rocky, there's the Jovian gas giants, there's the ice giants like Neptune, and there's the small icy outer worlds like Pluto et al. And we go, oh, okay, there's certain flavors. And if life is self-assembled, would we not see these similarities? So we come to curiosity at Gale Crater. And we saw in this lovely video Scott found for us, friends, that showed, oh, here's Mars wet, here's Mars dry. And we see that, oh, Mars used to have a lot more water. And they say, oh, 87% has been lost to space. But we also know there's quite a bit of water frozen and trapped that went into the crust as opposed to out into space. So that indicates there might be even more water. And so you go, wow, Mars could have been, and I found it fascinating. When they did that animation with Mars with the water on it, every place else was a desert. And then there was the ocean. And then everything else was a desert. And I'm like, if it had water, if it had a water cycle, which certainly with that much ocean it would it indeed, was it indeed rain falling on lifeless rocky plains? Or does life self-assemble? Would not early wet Mars have been green? Or if some other type of chlorophyll type molecule was selected, we know we have red and yellow and green and purple chlorophylls. Might Mars coloring be different? Maybe. But I found it interesting. They said, no, there's water and then there's desert. Which
we need
there
to
are
find
places
some
like
fossils. We need fossils.
Yes, there are places like that. So curiosity is in the Gale Crater. And we're not talking Perseverance. We're not talking the new rover here. We're talking about the old rover, you know. Curiosity has been on the ground for 9 years. It makes me feel like an old guy. Well, hello. But it makes me feel old. I'm like, holy cow, curiosity's like the new kid. No, it's not. And even the new kid, even Perseverance has been on the ground for 2 years. So Curiosity has been in Gale Crater for 9 years, and it's been traveling around, and it has been grinding, drilling, pulverizing rocks, and then it has the ability to use this lovely onboard laser system, which vaporizes pulverized rock. And what they've found, and they've taken rocks out of lots of different areas, and they found many of the samples, let's just say many, let's not exaggerate anything. Many of the samples show the same excesses of carbon-12 as the Australian specimens from Tumbiana. Now, the scientists on the video said, oh, well, what was happening? We had this concentration of deuterium. Why? Heavy water is heavier, right? With deuterium instead of hydrogen in the H2O. It was DHO. Well, that makes the water molecule heavier. It's harder to vaporize it and send it to space. And so we find this concentration of deuterium. Well, is there some kind of atmospheric process that concentrates carbon-12? We know of no such process on Earth. There is no atmospheric process on Earth, and nobody in a laboratory on Earth has done a simulation of Mars' atmosphere, mostly CO2, mostly very dry, very thin, bombarded by UV because there's no ozone layer on Mars. And so they get as much UV as we do, even though they're farther away. And could this somehow concentrate carbon-12? Nobody's been able to demonstrate this on Earth. Nevertheless, the hypothetical, well, it could happen in some way we don't understand because Mars is different. Mars is different indeed, but chemistry and physics tend to be universal. And I always kind of, I have this creeping feeling when somebody says, oh, there's a chemistry that exists in another planet on the surface, which is unlike the chemistry on the surface of Earth. Really? Really? Now, interesting, one place where that has been found, they have found that indeed and this we're talking deep interior of Earth in the mantle, there are different chemical processes and different forms of matter, different crystalline forms of matter that exist in those very high temperature, mega atmospheric pressures of the Earth's interior. There are different chemistries and different things that go on in that very high pressure, high temperature environment. Okay, we're talking temperatures, 2,000 or 3,000 degrees centigrade, certainly well above the temperature needed to melt rocks, even at those pressures. We're talking pressures in several, million atmospheres or more. So crazy high pressures, crazy high temperatures, and under those extreme situations, circumstance, molecules form different structures. And I'm like, okay, but we take a look at the surface of Mars and the surface of Earth. How different are they temperature-wise? Well, maybe 50 to 100 degrees Celsius, not that terribly different, compared to the Earth's interior, right? The deep mantle and the core compared to here. How much was the difference of pressure? Maybe 100 times versus the millions of times pressure difference we have between here and the Earth's interior. I think Mars is more similar to us than it is different. And if you want to talk about a scale of pressures and temperatures from deep space where, say, Webb is, 350 degrees below 0 centigrade, and you talk about the temperatures on the interior of Earth, Earth and Mars are far closer than, say, Earth and Webb, or Earth or Mars and the deep interior of the mantle. Mm-hmm. But these are speculations, friends. These are speculations. What is true is many of the samples from Gale craters show the same kind of carbon-12 excess as the Tumbiana biological fossil samples on Earth show. So the question comes up, is this a biosignature? Paul Mahaffey, who's with the Goddard Space Flight Center, calls this tantalizingly interesting. I agree with him. It is tantalizing because it says, here's a real possibility, and here's something that looks like something that on Earth is absolutely a biosignature. And so, is it? Well, again, one data point does not make a graph. One data point is a dot. And we can say, ooh, it's an interesting dot. It's in an interesting place. But it's still one data point. And
So what do you think, Daniel? Do you think if they find something and they're able to bring it back in the tubes and we're able to explore it here on Earth, and they find something, they go, my God, this is the gotcha moment here. This is what we've been looking for. Do we still need to go back up there and verify it somehow?
Yes, absolutely. My prediction, let's say 10 years from now, the sample return mission comes back. Scott, you and I are still, grace of God, around to be on this show and argue about it. And they open it up and scientist A says, look, the carbon-12 ratio, and now I find nanotubules. I find structures which can only be biological fossil in nature. And immediately scientist B will say, you are nuts. These are geologic formations. Right. I just need to see if I can find a process that will reproduce them to prove you're wrong. And in fact, finding a abiotic process that would produce something is not an indication that life did not produce it. It just says there's two alternative ways to produce it. The Allen Hills meteorite, people have been arguing over it for
a while.
3 decades, and there is no consensus. So I think if people go back and find in sample return, ooh, look, I say microfossil, you say geological process, and I think it's going to take, excuse me, I think it's going to take boots on the ground. I think people are going to have to be there, and they're going to have to dig with hammer and shovel. They're going to have to examine things. They're going to have to say, wow, this is interesting. Look, here a few centimeters over, here a few meters away. They're going to have to do things with the mobility and flexibility that rovers do not have. Rovers cannot do, they do amazing things. And my new and snazzy hat is off in wild cheering to the engineers who build the rover systems. Oh my God, how awesome is that?
Yes.
But it's not men and women on the ground doing science. I think probably the only way the argument will be definitively settled is if somebody says, oh, look, under the microscope, that's a cell. There's a microbial mat. We had sterilized tools and we dug down into the surface deep enough. We found liquid water underneath, and look, something swims by the camera lens. I think if we find extant life on Mars, we're going to immediately reinterpret a lot of this past evidence in a new light. And this is what happened. Galileo said, oh, Copernicus is right, and the sun is the center of the solar system. And there was a lot of naysaying, and yet at some point there was an accumulation of evidence where there was a tipping point and everybody said, oh yes, and then there was a great reinterpretation of past evidence. People went back and looked and said, ooh, look, this was really that, wasn't it? He must have seen this, mustn't he? And we see this all the time. We see people going back and looking at things that Newton did, Galileo did, Copernicus did.
Right. Which is why all this old data is worth preserving.
Oh, yes. Cassini hypothesized that the moon Iapetus around Saturn had one leading edge, which would have been darker than the trailing edge, which would have been lighter. And that's why it had different albedos. And it was what, 2.5 centuries. It was centuries until we sent a probe to Saturn. Well, yep, look at there. This moon looks like somebody painted one half and got bored and stopped. And we understand why now, tidal locking and all of that. But there's going to be a big reinterpretation of evidence once we get something definitive. Could we find fossil evidence that was indisputable? Yes, I suppose so. We find something that looks like a leaf or a trilobite or an insect or a fish, and we'll go, wow, look at this. That's a fish. That's a swimming animal of some kind. And if you're dabble in paleontology, you know a lot of the ancient animals didn't look like modern ones, but it's still clear this is a swimming animal. And big ocean, okay. Might we find a fossil that's indisputable? Yes, but if you know anything about paleontology, excavating a fossil like that is a large endeavor that requires not, machines can't do it. It takes long man hours, and you have people digging and excavating, and it not only requires, let's bring in a bulldozer, it requires people with little tiny brushes and dental picks to excavate these fossils. So I don't think a rover, God bless NASA, ESA, the DLR, and all those folks, God bless them, and go to it, folks, because I love to watch this stuff. I don't think it's going to settle the argument. And so we look at this and we say, wow, what are the hypotheses for this? And we say, oh, well, there's one. There was ancient microbial life on Mars, and it caused carbon enrichment. And as we've talked about, is this possible? Yes. Do we have definitive evidence? No. Do we have things like the Allen Hill meteorite, which nobody can agree on here? Yes. The Viking lander. I'm in the camp that says Gilbert Levin and Patricia Straight discovered biological microbial life on Mars. I'm in a minority. That doesn't mean I'm wrong. Galileo was in a minority too. Data. I can say what I believe, but can I prove it? No, it's an hypothesis. It's a supposition at this point.
Right.
The second question is, if microbial life, from the other side, if microbial life did exist, why don't we see stromatolites or other simple microbial mat fossils? We're not sure. Maybe we could just not be in the right place. These places where we find these stromatolites are quite rare on Earth. We don't find them commonly. The other thing people say as well, if there were these microbial mats, they could have produced a lot of methane, which would have been carbon-12 enriched. The UV in the atmosphere would have made this synthesize into more complex, bigger, heavier molecules. That would have rained out over the surface. And so we could see this carbon-12 enrichment incorporated in the rocks, well away from where we had the evidence of microbial activity in microfossils on Mars. The question, could unique Martian atmospheric conditions combined with UV light create enriched carbon-12? Nobody's been able to demonstrate this in a lab on Earth. And we can certainly simulate Martian conditions easy enough. The only thing we can't simulate is these processes playing out over thousands or millions of years. But nobody's been able to find a process that even looks like this. Could Mars have traveled through an enriched cloud of carbon-12 dust that enriched the soil of Mars? Well, we have seen clouds near the galactic center which appear to be enriched in carbon-12. How good is that data? Don't know. Have we ever traveled to the galactic center to sample these and see, to get ground truth? No. When we talk about these spaceborne, when we talk about nebula, Scott, we're talking about things which are tens, hundreds, millions of light years wide. Right. Could Mars have been affected this way where we don't see it on the moon? The
Good
moon,
question.
we've looked, we see no evidence of carbon enrichment or anything like it on the moon. We see no spectroscopic evidence on Mercury. We see no
The
spectroscopic
moon has a
evidence
very,
on,
very thin atmosphere, so maybe, you
right, an
know,
exosphere. But
right?
carbon doesn't vaporize off a planetary surface very well. What about Titan? Titan has a similar atmospheric pressure to Earth. It has dunes. It has an aquifer. Okay, yeah, they're all liquid hydrocarbons like butane and methane. But gee, if there was a carbon cloud, wouldn't it have enhanced carbon-12 lying in the sands on the ground? I would think. If our solar system passed through a cloud like this, would we not see evidence of it on all the planets? Number one. Number two, would we not see evidence of carbon clouds this far out away from the center, which nobody I know of has detected? It's been near the galactic center. Again, you know, curiosity has tested lots of different things: mudstone, sandstone, dune soil. They've drilled into rock walls and craters. Heating, they have this wonderful tunable laser spectrometer, heats stuff to 1500 Fahrenheit, vaporizes carbons in the pulverized sample. And heating doesn't change isotopes, Scott. Heating doesn't change them at all. For heaven's sakes, if that were true, atomic weapons and atomic power plants wouldn't work because those operate at very high temperatures. The other interesting thing, and I don't find this to be as nice or as friendly, some of the scientists at NASA say we should have an official scale
Yeah.
to evaluate biosignature evidence. Up to that point in the sentence, I'm good. Oh, we should have a scale, as in weak evidence to strong evidence, right? Up to that point, I'm good. But the finish of the quote is, we should have a scale that is used to evaluate biosignature evidence before it's released to the public. I don't like it. NASA has always committed to, these are taxpayer-funded missions. It's the public owns the data.
Why would
That's
they do
why
that?
we're able to
Why-
put
why
these
did-
little
why do
videos
they-
on How Do You Know?
What's the motivation?
Well, the motivation, and this is a quote from Mark Kaufman on a NASA blog called Many Worlds.
Okay.
The emphasis on providing both a biological and abiotic explanation is very much in keeping with the evolving NASA efforts to rein in claims that extraterrestrial life or signs of past extraterrestrial life have been found, unquote. I'm sorry, I don't see this as NASA's place to
Right.
rein in interpretations they don't like. Data will answer this question in time, one way or the other. And you've either been on the right side or the wrong side, but either way, science is self-correcting. And what they're saying here is we don't trust science, we don't trust the scientific process, we don't trust the public, and we've got to control information. I'm sorry, this sounds way more Orwellian than it does scientific. I really don't like it. It raises the hackles on the back of my neck. It makes me think Pope Urban VIII. Galileo, don't you write any more about that nasty Polish guy. Just don't do it. We're going to repress you. We're going to control the interpretation of this evidence. We're going to control what evidence is released to the public, and we're going to decide what the public should know and what they should think about it. That's not science, Scott.
That's
That's
politics.
nothing like it.
It's politics.
Well, that's the politest non-cussing word I can think of for it. Censorship is another one.
Right?
And it basically says, I don't trust the public and I don't trust my fellow scientists. Which to me, it says a lot more about the people who come up with this crazy idea than it does about the scientific process or the data.
Right.
I don't like it. We've talked about methane gas before, and methane gas is a biosignature. On Earth, it certainly is. We've detected methane plumes on Mars. We've detected big ones from ground-based telescopes. We've discovered methane plumes from Curiosity. Obviously, they were much smaller than the big scales. And then there's the ESA/Russian trace gas orbiter, which has never detected any methane. But it only looks at the upper atmosphere where ultraviolet would quickly destroy methane. It doesn't look at the lower atmosphere. And so the data is mixed. And we don't yet have enough data to say, this is the lens through which we should view these results. Or this is the theory which unifies and explains all that we know so far. This is why true theories are magnificent scientific achievements. Often the work of maybe a single genius, but in modern times, more often a huge crowd of people. There's one seminal idea, and then a huge crowd of people goes off and investigates. Higgs boson. The Higgs boson, one of the most cited papers in modern physics, had 1,600 co-authors. And we know the one fellow, Higgs, had the idea in the 1960s, and he got a Nobel Prize for it. But the discovery of the particle took a literal army of scientists. And now that we've discovered it, we have this framework lens, and we can go back to all the past data, and we have a framework, a theory which explains everything we know and everything we've found. This is the way science works. And when I see, much in keeping with evolving NASA efforts to rein in claims for this theory or that theory, I'm like, oh gosh, guys, you're on the wrong track. That's just mistaken. That's a huge error. It's a step backward. It's not science. And as Reagan said, this idea will end up on the ash heap of history. And I have certain things that I'm gung-ho about. I believe Gil Levin and Strait discovered microbial life on Mars. I believe Pluto is a planet, and I argue with people who say it isn't. And I have my certain scientific horses, theories that I put my money on, and I'll die on that hill, as it were. But I would never say I want to control the way Scott Roberts or anybody who watches How Do You Know, I want to control the way you interpret this evidence we present on this show. No. We give you lots of data and information, and we put lots of links. Go learn more about it. And I want to hear your comments. Doc, I think you're off base. I love that stuff. That's great. That's the kind of rigorous, productive scientific debate that eventually solves these questions. But censorship never will. Anyway, have we got any fun comments today?
Yeah, there's lots of comments here.
Yay!
Okay, so let's kind of go back a ways.
I've provoked my audience once again.
Yes.
Hooray!
Something has to do with meteor impacts. Josh Kovac says, how much impact does planetary gravity have on ambient chemistry?
I've not seen that gravitational fields per se have any. Pressure does, and gravity can create pressure, but gravity itself, I don't think it has any.
Okay.
I've not seen anything in the literature, and I taught chemistry, basic intro chemistry for many, many, many years,
Okay.
and physics as well. And I've never seen anything in the literature to say, but then again, testing this on Earth would be really, really difficult. We have one gravitational field we all share. Thank you very much. We can create simulated high gravity situations, such as centrifuges. But I've never seen anything either that say there's different chemistry, and we can get centrifuges that can go up to 100,000 gravities. We have ultra centrifuges.
Okay.
And those things, I've worked with some of those things. I worked at Caltech as a research worker for a while, and we worked with an ultra centrifuge. And it was astonishing. We would use it to separate out virus particles of different sizes. 100,000 gravities. This thing spins in a vacuum, looks like a big commercial washer, has a vacuum chamber inside. You have to balance everything to a hundredth of a gram, because if it gets the speed wobble, it's really, really bad. And when it's spinning at those kind of terrific rates, no indication I've ever seen that the chemistry in a centrifuge was different than that.
Okay.
Just in a test tube on the counter.
Harold Locke says it does boggle my mind that underground water is being overlooked and only a small amount condenses on the surface.
The current indications is that there's enough water under the surface of Mars to cover the planet 10 meters deep. And certainly Mars has topography, so that would concentrate in oceans. But the indication, they were just looking at how much water has left the planet versus how much remains. I don't see any indication that they were talking about underground water. And I think that's a hole that they need to address. And I think 20% of the surface covered may be underestimating it significantly.
Okay.
But
Martin Eastburn says, did the carbon come from a star or did it come from ejecta from Earth?
the carbon we see in our solar system all would have been forged in stars and then ejected in a supernova type explosion and then incorporated into the cloud, essentially contaminating the nice clean hydrogen helium cloud. And that's how second and first generation stars are able to form planets, where third generation, the very most ancient stars, which were pure hydrogen helium, because there were no other older, bigger, heavier metals. Astronomers, astrophysicists call everything above helium a metal. There were no other heavy elements that had been produced yet. So Carl Sagan's famous quote, "You are made of star stuff," very much true. And we think now that some of the platinum series metals, platinum, gold, silver, other things like that, may have been produced in white dwarf novae rather than in supernovae. And that's all fine, but all the carbon generally produced in carbon type stars, and boom, the star goes bang, the carbon is ejected, and carbon becomes incorporated into both biological and abiological processes as planets form. And it's one of the lighter elements. Keep in mind that as planets melt and differentiate, the heavy stuff like iron and nickel sink in. The lighter stuff, which includes basaltic rock, illuminates, magnesium, carbon, nitrogen compounds, all of these float to the surface and exist on the surface primarily. It's a question whether how much of these lighter materials at all you would find, but keep in mind, what's the deepest we've bored into the surface of the Earth? 10 kilometers, 12, something like that?
Yeah.
And we have not very far. Not very far. If you were talking about an orange, that wouldn't be a pinprick. That wouldn't break the skin of an apple. We haven't gone very far at all.
Lots of comments of, when you were discussing, how some scientists would like to withhold information, I guess, till they get it figured out or something, so, right? So Joe Stromatolite says that they're trying not to be the object of conspiracy theory. I've got some news for them. Harold Locke says it's a fascist mind control.
I would
says, trust the
hope it doesn't
science.
quite go that
Pluto
far.
is a planet.
Yes, I think so. And maybe we should do why Dr. Barth thinks Pluto is a planet show. Maybe that would be a fun, rabble-rousing show for episode 50.
That's right. Joe Schmuckatelli says the fact we're discussing this is a good thing. It's out in the air, even if the data isn't.
Yes. Yes.
And another comment, that doesn't happen in thought-controlled society. Josh Kovac says, planet is a marginally useful designation.
True.
And Says dwarf planet is still a planet. I agree with that. And Joe says, thanks, Daniel. Fantastic presentation. And he says, I love to hear your rants on life on Mars. so there
I
we
make
go.
no claims to be an unbiased source of scientific data. I make no such claim, and it's silly that anyone would even think so or accuse me of that after 44 shows. I present science and data, but I also present my opinions, and I try to make it very clear when I'm bringing up, here's established fact, here's what I think about it. I try to be very clear with people about, I want to distinguish that. And my opinions have value, I hope, if you come to trust me and value what I have to say and my point of view on things. I hope my opinions might have some value for you. Other people who decided that I'm a nut job a long time ago may have less. But certainly I do try to distinguish very clearly between fact, opinion, what I hold as an hypothesis, and what I understand to be a scientific fact or an established theory. And science has ambiguities, my friends. Science has ambiguities. And I always cringe a little when I see people trying to avoid or hide the ambiguities. And when somebody says we need to rein in claims, no, you don't. No, you don't. The scientific process the scientific steamroller will flatten that lumpy, bumpy surface
Otherwise,
into
it's
something
not a very
smooth.
good process if it can't.
Yes,
right?
it's a brilliant process. It's been working well, thank you, for millennia or more. And we go by data. And it's true, every once in a while, we have a lot of ambiguous data. And until we get a seminal fact or a seminal experiment, which lets us, all of a sudden, it cleaves the diamond and it falls away neatly, and we suddenly go, oh, that's how this theory now interprets. And I'll go ahead and throw in one of the most venerable, the standard model of particle physics. Throughout the 20th century up through the 1970s, 70 years, oh, every time you turn around, a new particle is discovered. Oh my God, how does this fit in? And now we have this very nice theory, which is precise to something like 10 decimal places. And they're struggling now because they're finding some particles which are heavier than they're supposed to be. And oh my gosh, how can this be? And they're going back and they're tweaking the model. But once they got the model, then they go, oh, look, all this data nicely falls into place now under this theoretical framework. But until you have that breakthrough moment to say, oh, we're going to rein in the idea that quarks are real and claims that there are quarks, and we're going to rein in. This is nothing for a government agency to do. It smacks of thought control. And I will be generous and I will say I'm certain that our friends at NASA, public employees that they are, have the best of motives when they do this stuff. But I think they've put their foot in the cement bucket, and they're not going to be able to extract it easily, and it's going to be messy when they do. You need to just do a full reverse on that. This idea that NASA should control how not only scientists but the public interpret things, that's terrible.
Can't be done.
It cannot be done. For one, you're quite correct. It cannot be done. And if anything with conspiracy theories has shown us, the minute you try to control it, it's like trying to control a jelly sandwich with a hammer. It's just, no, it's going to.
Yeah, you might get away with it for a while if you're really good, a few decades, but not forever.
Well, isn't that the basic argument against the conspiracy theory that we didn't go to the moon? That tens of thousands of people working to send the rockets to the moon, and hundreds of thousands of scientists examining the data, not to mention the brave men who went there and returned. Just disregard the astronauts. If it was a fake, you couldn't get these hundreds of thousands of people to keep the secret for decades. It's just silly. That doesn't happen.
Right.
And this effort from these folks at NASA, and there's a link, by the way, to the papers in there if you want to go read their arguments and see if you agree with them. I think it's misguided, and that's an opinion.
Ha!
That's an opinion, but I think it's a sound one, and I think history bears me out in this. That restricting the interpretations of data is never a path to productive science, and it's not effective as thought control either. But in terms of the goal of scientific organization should be to advance scientific knowledge. And I don't see that restricting access to information or interpretations of it is ever a pathway to effective science and discovery of new things. And I just don't see it as an effective path forward.
Right.
And if you say, oh, but there will be commotion. Hello. It's an era of social media. There's always commotion.
Yeah.
There's always some crank on the
Science is
internet.
always a sausage factory anyway, so.
That's right.
Right?
There's always some crank on the internet in a snazzy woolen cap.
Yes.
And folks, for those of you who like my snazzy woolen caps, here's a new one. So I know I have fans and people when I did your show at your studio, where's Dr. Barth's snazzy cap? So a new cap, friends, just arrived this week.
There you go.
So there you go.
All right. Well, Daniel, thank you so much for today's show. And
You're welcome.
we look forward to next Monday.
Indeed.
We will, I do want to mention that we have a Global Star Party tomorrow night, Global Star Party number 92, and it's about shadows and illumination. So,
Yay.
yep.
Sounds great.
So there's,
And of course, as usual, anyone who wants to contact me, whether it's about theories about Mars or to learn the name of my haberdasher, can write to me at astronomyforeducators@gmail.com. And I hope you folks will go ahead and pre-order Star Mentor, which is due to be released soon. And
very soon, right? Yep.
Sorry?
Very
Yes,
soon.
very soon, this month. I am told this month. And Scott and I will talk about some sort of fantastic and exciting giveaway.
Giveaway. That's right.
And I think episode 50 sound like the plan?
I think so.
I think so. I
We're
think
getting
that
close.
should be enough weeks away that we'll have copies of the book in hand, and you can tell me what you would like, and I will inscribe it for you, and we will get them sent out. And hooray! What a celebration! Thank you, everybody, and thank you, Scott, again for the show and for being my co-host. Love it.
Thank
and
you.
We'll see you guys next week.
Great. Take care, Daniel. And for everybody else, thanks for watching. How do you know? And we will be back tomorrow with more programming, including Global Star Party. So keep looking up, and we'll see you soon.
Okay. Bye-bye, everybody.